In the complete machine, the sample area in front of the robot will be filled with racks containing tubes of blood. The robot is commanded to pick up a specified rack and put it on the belt. The belt moves the rack to the mixing station and then to a sampling station, which isn't in this prototype. After sampling, the robot removes the rack from the belt and returns it to its original location. The pickup arm must move straight into the rack to engage its pickup tabs. The robot's x-axis movement easily does this when grabbing a rack from the sample area. Sliding the rack onto a belt tab requires y-axis movement, which the robot must simulate by coordinated x-translation and theta rotation because it has no real y-axis movement. At the mixing station, pneumatically actuated mechanical fingers grab the tubes. The tubes are pulled out of the rack and inverted, typically 5 to 10 times, duplicating the mixing that would be done by a lab technician. In the real machine, the belt would then move the rack to a sampling station where blood is vacuum aspirated from each tube through a needle that punctures its cap. Y-axis movement must also be simulated to grab the rack in order to remove it from the belt. This is particularly challenging. At this time, both x and theta are accelerating, and the ideal ramps for them individually will not combine to produce ideal y movement. Most engineers would be surprised to learn that this synchronization is not achieved with a dedicated machine or motion controller, but with my general-purpose robotic mesh system. The sample handler is just one part of a complex medical instrument. My robotic mesh coordinates, without any dedicated subsystems, all mechanical, data acquisition, and communication operations throughout the instrument at this level of precision. Combining precision and flexibility typically is expensive, but the robotic mesh produces, in a fraction of the time, systems that are cost competitive with dedicated machines. I have achieved this by making the robots virtual. All robots in the mesh speak the same control language, which includes expressions for expensive hardware like motor control and data acquisition. Any robot can execute these, but if it doesn't own the resource, the system automatically sends a message to the robot that does own it. Local control is faster, but not required. To make this all work, I designed a unique mesh communication network and 2 languages. The control language, which robots execute, tells what to do. The configuration language describes everything in the machine. The control language automatically changes to reflect what the configuration language describes. Robot firmware is stable because every resource is an instance of a general class, which doesn't change even for vastly different machines.